And suppose this is the point where omega is 10. So this point will shift over here if it is minus j omega t. It's a delay. If it's a plus, it's advance. And in the physical system, there is no advance because systems are mostly causal. So this point will shift on this side by angle 10t. So what will happen? And as you go up, omega becomes million. This angle will be in millions. It will be multiple circles, hundreds of circles. And this graph can become like this because of the delay. I'm not going to plot this line, only this line. So this graph can become like this. Many crossings on this real axis. And what is the condition of the stability? The outermost crossing should not cross -1. Why many crossings? Because you go in and in and in. Closer means you go up and up on this imaginary axis. Go up means you're getting over here. So there will be a huge subtraction of angle in term of because of this constant delay in time. Suppose omega is a million and t is 1, so it will be a million radian. Million radians are many circles. So there will be multiple crossing of this negative real axis for a system with the delay, and without delay this was a perfectly stable system, but with delay it can become unstable if the first and outermost crossing is not encircling -1. So this is the way it influences, the delay influences the system which are uh, perfectly stable and try to make them unstable. And that's why and system with the delay, we design the system for a system with the delay, we try to design the system accommodating all the delays, and with the delays we try to fix the phase margin and gain margin of the system and try to make them positive. So in this context, what you will do, there is a good example in the book. This is hot ingot robot control. This is a system with a delay. There are two poles at s is equal to -1 and s is equal to -1. Two poles at -1, and there is a delay st. T is pi by 4 second, approximately 3.14 over 4, which is I guess 1.6 and 0.78 second delay. And the design specification are that steady state error because of the step should be less than 10%, phase margin more than 50%, percent overshoot less than 10%. Remember, because of the delay, because delay subtracts the angle, the phase margin reduces, and for the system to make it stable, we have to reduce the gain, to reduce the gain crossover frequency and improve the phase margin in order to make the system stable. But if we reduce the gain, then steady state error becomes huge. So that is the contradictory type requirement. If you want to reduce the steady state error, you increase the gain, you increase the system gain, loop gain. But increasing the loop gain, it will reduce the phase margin and try to make the system unstable, improving the. So go through this example. This is example 9.11 in 11th edition. I don't know what is the corresponding example in some other edition, but go through this example. It's a very good example, and the system is designed with the delay, and these are the polar plots, Nyquist plot, and see there are many crossings, and this equation is plotted. This equation is derived, which has multiple solution. This is basically the imaginary part, which is put equal to zero, and the solution of this it has infinite number of solutions, which is the graphical, which is the method equivalent to the this graphical representation, which has many crossings of real axis. So go through this example in your own time, and if there is some problem, you can directly consult me in the class. I'm not going to go through the detail because this does not have any unique answers, but it's a very good example. And with this, we'll finish the chapter 9, and in the next lecture, we'll start chapter 10, which is the compensator design. Lead die compensator, you have gone through the lead compensator. Anyways, I'll cover that in the lecture, and then we'll do the lag compensator. Okay, thank you so much.